by Professor Philippa Mason, who is the research coordinator of the ERATOSTHENES Centre of Excellence. And then we will proceed with our invited speaker. I would please ask you to turn off your cameras and microphones, besides whoever is speaking. If you have questions, please type them into the chat. We will read and answer your questions after the talk. Thank you. And if you're ready, Professor Kyriakidis, the floor is yours.
Thank you, Thanaida. Yes, it is with great pleasure that we welcome Dr. Philippa Mason to this week's webinar of the ERATOSTHENES Excelsior team. Dr. Philippa Mason is a senior lecturer in the Department of Earth Science and Engineering at the Imperial College London, and she has received her MSc from University College London and her PhD from Imperial. She is a professional field geoscientist and a specialist in remote sensing with more than 20 years academic and commercial experience, and with research interests in the application and development of InSAR, in geohazards, tectonics, and spectral geology and image processing on Earth and other planets. Her teaching and research at the Imperial College involves the translation of terrestrial Earth observation techniques such as Interferometric Synthetic Aperture Radar and imaging spectroscopy to assist in understanding geological features and processes on Earth and other planets. She's a member of the engineering scale geology research group, whose research activities are focused on the development of InSAR tools for the measurement of small-scale ground deformation and in urban and rural settings. And she is also a science team member of EnVision, an international UK-led mission which will take Earth Observation SAR technology to Venus in 2031 to help understand why it is so different to Earth and establish whether it is technologically active and if it was ever hospitable for life. With this, thank you, Philippa, very much for this, for the time that you spent here for this talk. And we hope that you all find this exciting, at least for other planets and for Earth. And we look forward to hearing what you have to say. Thank you.
Thank you, Professor Kyriakidis. Dr. Mason, the floor is yours.
Okay. Well, thank you very much for the introduction, Phaedon. Thank you very much for the invitation, all of you. This is a very pleasant and exciting thing to do. So I'll just share my screen so that I may begin. Oh, there we go. Hope that's visible. Need to get rid of all that so I can see everything. There we go. Perfect. Do you see? Is that everything okay there?
Yes, fine.
At your end?
Yes.
Perfect. Excellent. Well, thank you very much again. And so yes, I'm very much on Earth today, and so I'm presenting this talk on behalf of our team of researchers. 3 of us colleagues, originally only at Imperial College, and one has now moved to Royal Holloway University, but we still work together. And we have a group of PhD students working on a variety of complementary topics, the majority of which are working on InSAR. And you can see from the logos on the bottom of the page that much of this work is supported financially or in one way or another by a variety of organizations, some private engineering firms, but also some service companies, pardon me, and some technology development companies like Airbus. And so they're helping us in one way or another in our attempt to further the tools that we can use to help us in engineering geology, in monitoring infrastructure, but also in the wider environment. And most of us are, well, let's say James, Richard and myself are geologists. So our interest has come sort of initially from wanting to understand processes going on in the subsurface by monitoring changes in the surface itself. So we're very much interested in picking up undiscovered, unmapped faults in the ground, understanding how the ground responds to engineering works, to water moving in the ground, whether that's man-made water movements or natural ones. So we're concerned with all of these things together, and InSAR is the tool that we're developing to improve the reliability of the retrieved measurements of the ground that we can make, and ways to better understand the results that we get and what they actually mean in terms of the geology. So that's kind of where we are. So what I was going to talk to you about today, and some of this, some of you will have seen before, but not all of it. So what I'm going to talk today about is, I'll just briefly mention the team in a minute. Is about basically the employment of time series persistent scatterer interferometry, which is our solution to the long-term monitoring of the ground to understand the geotechnical response to a variety of different phenomenon. So we're sort of mainly, I'll show you some examples of the work we've been doing using persistent or point scatterer InSAR in urban areas. And then, so the tools that we've been developing to assist in better understanding what we call distributed scatterers in rural areas, which is the challenging part of using InSAR in the natural environment, is to be able to do that in areas which are quite tricky, vegetated, and changeable, and a variety of case studies from the UK and around the world, and a little bit at the end about some of the new things that's coming out of this work. So that's the idea. So the most important thing really is our team, which consists of 6 students who are working on InSAR development in one way or another, and a series of other complementary studies which are more geological in their focus. And Stuart Agar has nearly completed his PhD, and he's developed with us our own in-house processing chain. Hence, this is the reason why we're now able, like many other InSAR service providing organizations, pushing the limits of what InSAR can produce for us. And then Jenny, Goshia, Sijao are testing out using the tools in a variety of different settings, coastal environments, desert environments, looking for ground disposal facilities, or in urban areas, monitoring tunnel projects, etc., things like that. And Anthony is working on the development of drone SAR and drone InSAR, which is particularly challenging. And Robert is working on improved atmospheric modelling. So together we have a great team, and the work I present is a collection, a selection of some of the things that they have all been doing around the world. Imperial College has quite a long history of remote sensing, but in a very sort of kind of scattered way, in disparate ways across the college, different departments, different disciplines. And just a couple of years ago, myself and a couple of others formed a research network to kind of foster interdisciplinary, interfaculty research activities, and to collaborate with people like yourselves and other organizations, and perhaps be able to make bigger bids for funding, commercialize things. And so the Earth Observation Network, we're pretty proud to sort of get going right now. And we have a new seminar series, and very happy that Professor Hadjimitsis is going to be talking tomorrow in the afternoon on your Excelsior project. So there's lots of hopefully fruitful things to come from this collaboration in the days to come. And so we're predominantly using tools, data sets like Sentinel-1, largely because we're academics and it's freely available, but it's also routinely collected, and with Sentinel-1A and 1B, it's a pretty regular temporal collection period, revisit period. So we have data for every 6 days, and that's not real time, but it's getting close to being able to provide the regularity of observations in a time series, which is particularly useful. So we're using other data sets as well, but Sentinel-1 is basically our workhorse data. I think everybody's familiar with the idea of using InSAR now to monitor motions of the ground. And it's come a long way from that first image of that first interferogram of the Landers earthquake that appeared on the Front of Nature in the early 90s. It's come a very long way to being a pretty much operational routine tool to monitor all kinds of motions, subsidence related, whatever, in urban areas and across the world, and in mine tailings dams and all sorts of applications. So it has become a very much an operational tool, but there are still areas of technical difficulty, particularly using InSAR in rural areas. So there's still developments to come, improvements in the precision and the accuracy of the measurements that we can make. And despite the fact that it's an operational tool, there are still communities who are a little uncertain about how to interpret InSAR results, what level of confidence they should attach to the results that they get. And there's a lot of debate about amongst service providers, amongst the community, about what should be provided to the public, to the user, the raw data, the process data, interpreted data. It's an open debate at the moment, and so there's still work to be done in making this a technology which is usable for everyone. And to that end, the European Ground Motion Service is a very exciting initiative under the Copernicus banner. It's sort of it's built over many years and is moving towards a pan-European service to deliver ground motion data from InSAR to anybody that wants it. And I think this is a tremendously positive move. It's a very important thing. And then there are really no standards in Earth observation across Europe in the products of the data, and that's something which again is being discussed a lot, and we're sort of taking part in this discussion in a small way by writing some UK guidelines, national guidelines on how to use Earth observation data in the field of infrastructure monitoring. So it's very much an active area, an important and active area that we're trying to contribute to in our small way. So for those of you who might not be all that familiar with the InSAR principle, this pretty much encapsulated. I've stolen this lovely diagram from Trey Altamira. So we have two observations, and a first observation and a second observation in time, from more or less the same position, because remember, satellite observations are very accurately tracked and their orbital position is well known. So we have two observations separated in time with potentially some motion that's happened between those two observations. And that motion is given to us, as it were, in a slight difference in the range direction between the two radar beam travel times. Delta R is a phase shift in the radar beam, in the wavelength of the radar beam, and that phase shift contains the amount of deformation of the ground. And this technique we refer to as differential InSAR, the differential phase of the wave between two coherent observations of the ground. So in that phase difference is over the two-way travel distance and the wavelength of the radar in cycles of pi gives us that precise amount of ground motion in millimeters, for instance. And the sensitivity of differential InSAR is sort of, it's sensitivity on a millimeter scale, but precision is on the order of centimeters rather than millimeters. So it's certainly good enough for measuring sudden significant movements such as you might get from an earthquake. But for monitoring things over time, small changes over time, we have a bit of a problem because the coherence of the signal is important, and coherence reduces significantly in time. Random changes to the scatterers on the ground, which affect the local spatial correlation, affect the coherence, they change, and that random change is cumulative. So on the right hand side we have an interferogram from TerraSAR X with an 11-day separation. So two coherent images of the ground, separated in time by 11 days, and there you see that the BN there at 100 meters is the distance in space, so they're quite close together. So the importance of that being that any change in the phase is really to do with the change in the ground, not in the change in the geometry. So if we look at the 22-day interferogram, it's a little bit more noisy. And the very, very noisy area in the bottom is the sea, where we have no coherence at all because the sea is constantly changing. If we look at 33 days, then we see we're really reducing the coherence. Only a few patches of coherent interferogram where the urban areas are on the coast. 55 days, it gets worse. And after a year, there's almost no coherence except in the urban areas. So there's this problem of reduced coherence and cumulative low coherence over time. So an interferogram with a long temporal separation is going to have very low coherence. So if we want to monitor motions in the ground that occur very slowly on a potentially millimeter scale, over many SAR images over time, then we have to take a slightly different approach from conventional differential InSAR. So what we're looking for is stable reflectors, objects on the ground which reflect in a consistent way through the time series, and we try to monitor their behavior. The amplitude of the signal can change greatly between two images over time. But if we look at the phase and the amplitude, and we look at statistically how a particular object on the ground behaves over time, we can pick out what we call persistent reflectors, things like buildings, particularly good persistent reflectors, and they stand out above the background, and we can monitor them, we can track them through a time series, and they behave like little sort of natural occurring internal GPS, and we can track their positions in time and space because the assumption is that they're not moving. So we can look at their behavior statistically through the time series of many SAR images. So if you look at an urban area, and this actually is the Department of Civil Engineering in Imperial, and over the top of it, the coloured dots are the persistent scatterer measurements that have been extracted from a time series of sentinel data across that building, and you can see that they're distributed all over the place, but it isn't immediately clear exactly why points appear where they do, and it's very tricky to predict where persistent scatters are likely to be. But in an urban environment like this, where they've got buildings with smooth, flat, vertical and horizontal faces, lots of metal, lots of very sharp and hard surfaces, we get a lot of persistent or permanent scatterers, and we can, because they're not moving, they're not changing in space and time, we can track their location and use them to generate these precise measurements in time. So any object that is stable will give us a nice measurable radar echo. And using this technique, we can track very small scale motions of these persistent scatterers. This will be, and these motions will be too for differential InSAR. And if we're really struggling to find stable reflectors of this kind, we can use things like this sort of artificial corner reflector. There's a picture of which is on screen now. This particular one is actually sitting on top of the civil engineering building. Was put there by one of our students, and they're oriented in a particular way to reflect the radar signal. So by using these persistent scatterers, we can build up a really complex picture of ground change over time. And our first PhD student to work in this area, Christine, produced this image on the right, and it hit the BBC press in 2019 and was all over the Guardian and the Independent papers, and captured people's imaginations because it's so colourful. And she had a competition, I think it was called Science as Art or something like that. So it's particularly interesting because it captures the subsidence after the Crossrail tunnelling project, which is still not yet complete across London. But that red snaking line is the subsidence above the actual tunnel, and the slightly broader patches of red. Oh, actually, where's my laser pointer? I have the technology, don't I? Yeah, so it's slightly broader, brighter patches of red are where the stations are. So I believe that I think this is Bond Street station here, and what else? So Canary Wharf is over here, and this is Crossrail. And these other little things took some time for Christine to understand. And this is another utility tunnel, and this area here, I shall show this actually later on. This is the cone of depression, or let's say it's the ground response to the cone of depression from dewatering at Canary Wharf for all the construction that's going on there. And then conversely, this area, this blue area, is where ground is rebounding after construction and tunneling have finished and the dewatering has stopped. So largely, the ground is sort of kind of greeny colour. That's not really moving very much at all. But the yellowy colours are distinctly subsiding. But it's the Crossrail which captured everybody's imagination. And this image is made of entirely persistent point scatterers from the buildings. You see that the parks. So here is Hyde Park. We've got Battersea Park here, Regent's Park, Green Park, all the parks in London, lots of parks, royal parks, and the River Thames are black because there's no coherence. There are no persistent points. So they actually make quite a good navigation across this image, so you can see exactly where you are. But all the coloured points that are used here are entirely point persistent scatterers from buildings. One of the things we can also do with this kind of data we have from both the ascending and descending orbits of the Sentinel satellite, of any satellite, any Earth observation near polar satellite, and because the SAR is side looking, so on the descending orbit it's looking to the right or the west, and on the ascending arm it's looking to the right, but which is the east. So you have two opposite look directions. And so if you take the line of sight measurements from both those look directions and decompose them, you can extract then both the vertical and the horizontal components of ground movement. And this is particularly useful. So the implication here is that vertical movements can be associated with all sorts of phenomena, largely man-made, subsidence from tunneling, etc. But horizontal motions are quite odd and generally only geological. And because the the orbital tracks are near polar, and we have a side-looking technology. That means we can really only look at the east-west horizontal component. We're not sensitive, or very, very low sensitivity to anything which is a north-south movement component to it. But anything which is moving in the east-west direction can be a result. And Jenny's been looking at, London, but of course she's decomposed the Sentinel data, as well as the ERS SAR data from the 90s, and produced fascinating maps of motion. These are vertical displacements in London, and you can see that it's quite complex pattern. There are some large contiguous areas where the ground is responding in a relatively uniform way, particularly this red block and the Sentinel data, and it's also some blue areas which have quite linear boundaries. And she and one of our other students, Tom Morgan, have been using these data to compare with known structural information in the subsurface across London, and a whole series of geological hazards and new faults which have been unmapped previously have been discovered. And because Jenny's PhD is in collaboration with the Thames Tideway Tunnelling Project, she's been able to convey to them that when the tunnel boring machine progresses to a particular position, they're likely to encounter some buried hazards. These yellow areas here are fault zones which have been encountered by tunnelling projects, and she was able to pick out a few that they were not expecting. And she did the same thing for the horizontal motions, and again it's very interesting and complex, and very, very complex pattern which is difficult to interpret. The ERS data are particularly noisy, and there's not much in there that we felt we could really get our teeth into. But again, the Sentinel data are showing these contiguous patches which are apparently bounded by geological structures. So groundwater and the structural breaks, the structural discontinuities in the ground allow areas to move up and down contiguously and in isolation from other areas. So this has been quite revealing in our understanding of the geology beneath London. And geology in urban areas is tricky because you can't see the rocks. So you have no way really of doing any kind of geotechnical work until you hit something unpleasant. So it's quite a useful tool. We also have a student who's looking at coastal processes, and landslides and coastal erosion and coastal collapse are certainly very important areas of concern around the coast of the UK. And Gosia discovered that she was able to resolve the behaviour of one of these rotational landslides on the coast in Sussex, a place called Cowgap. And you can see the landslide in this image here. So the rear of the landslide is sort of where that red line is, and then this chunk here is collapsing. But the landslide itself exists over quite a large area. So this is the scarp, and the toe is sort of on the foreshore. Using Sentinel data and persistent scatterer InSAR, she was able to produce this data, and then on discussion we realized what's happening is that the rear of the landslide up the top is subsiding, but the toe of the landslide, which is on the foreshore, is rising up. So these blue points are where the toe is coming up out of the sea and heaving, if you like, and she produced these average time series. So the rear of the main body of the landslide is subsiding by sort of 50 millimeters over the time period, and whereas the toe is rising by only a few millimeters. So this was a fantastic result. They weren't expecting that. Initially, though, she was really looking at a cliff collapse, and although there were some interesting results at the beginning, she moved on from that because it was very challenging to derive persistent scatterer points on this vegetated cliff. But one other thing that came out of this work is that actually on the foreshore itself, these yellow stars are persistent scatterer points, and her data reveal that the foreshore is downwearing by some 6 millimeters or so over this time period. And we were only able to do that by selecting only the low tide data. The coherence for these points is actually extraordinarily high. These are chalk cliffs, but the materials on the foreshore are quite soft and eroding quite rapidly. So some quite interesting observations about and implications for platform downwearing, which is compared with other conventional methods doing similar work. Back to London again, and Christine's work. She was able to demonstrate that you could chart the progress of the tunnel boring machine under Crossrail by looking at the individual time series of a series of points. So on this image on the left-hand side is basically Bond Street Crossrail station is underneath here, and you can see all these red points which are subsiding. And the series of time series here, 1, 2, 3, and 4. So the top one here is number 1, and if you look at all the time series show there is subsidence occurring at a particular point in time, and that point in time changes in each of these profiles. So the actual point of subsidence shifts by a few weeks and months through time, and that charts the progress of the boring machine northwards underneath the building. So there's initially quite sharp subsidence, and then it slows down as the materials settle. But this is the first time that such data were used sort of forensically to demonstrate the impact of excavation on building response and ground material response, which is quite extraordinary. And this work has been published. And then to take you back to that very large subsidence bowl at Canary Wharf, where the ground has been dewatered actively whilst construction is going on, to show you this kind of forensicity. So these maps are time slices through the InSAR PS time series, and they chart dewatering and subsidence on the left, then the dewatering is turned off and the ground rebounds. There's the blue patch, then there's dewatering again and then rebound. And you can chart behavior in time pretty precisely to illustrate the effect of the dewatering. And in so doing, we discovered and had confirmed the position of a fault, an unknown fault in the ground at Canary Wharf, which was actually encountered in the tunneling. And one last example, quite a fascinating one, is the behaviour of the ground under the O2, the Millennium Dome, on the south side of the river, which is actually affected by that large subsidence bowl at Canary Wharf. And the Crossrail team were not expecting the subsidence to extend quite so far south below the river, but you can see quite clearly that the dome is affected and is subsiding quite strongly over the northern half or 3/4 of the dome. It's not the actual canopy itself, it's all the buildings and the cinema and the shops and the restaurants inside that are doing the scattering. And you can see from this cross-section, this time series cross-section along the line, that the impact of the subsidence is most profound at the northern part near A, and then it's not quite so noticeable as you go southwards. So Crossrail quite fascinated and a bit shocked to see this. If we look at very desert areas and use the persistent scatterer InSAR to look at ground response there, we find some unexpected things. One of our students is looking for stable locations for nuclear waste disposal in China, and he's looking at the Tarim Basin and has discovered that large granitic bodies, which were previously thought to be pretty stable and not moving, actually have faults on them which are active. And so the two images on the right represent the vertical and horizontal components, again, Sentinel data for this area, this really barren desert area. And you can see that there are these very block-bound contiguous ground motions, both vertical and horizontal, which are bounded by faults which are clearly moving. And this was totally unexpected. The movements are small, plus or minus a millimeter a year, very small indeed. But it's the fact that they're so uniform and bounded by the faults leads us to believe that this is good evidence of active fault movement. Slightly wetter now. One of the problems with the persistent scatter InSAR is when it's vegetated or it's wet, you don't get many points. So this is a tailings dam, and you can see the points distribution is pretty scarce on the left. So we've had to interpolate the map, interpolate the values to produce this map. And you can see around the dam there is blue areas which are rebounding or rising up, and some red areas which are subsiding. And we believe that this is to do with the dam being footed on glacial materials which are shearing and bulging and swelling up at the base of the dam. So this is a very worrying picture about this dam. I mean, expected to sort of settle, but there are some heterogeneities which are slightly worrisome. But this issue of few points in rural areas is a worry. So we're doing some work, and Stuart's been developing this to improve longitudinal persistent scatter, a point persistent scatter InSAR. So on the right is a PS InSAR map. These are the stable points in an area of South Wales. This is where I come from. And you can see that the PS points are where the cities are, Cardiff and Port Talbot, the industrial area, and a few other cities and towns along the valleys. And in between, rural ground, lots of vegetation, very low coherence, no persistent point scatterers. So like everybody else is working in SAR, we're trying to develop ways to improve retrievals in rural areas. So we come back to this idea of improving traditional PS InSAR and tracking of the phase behavior throughout a time series. This is what we're trying to deal with, is areas which are rural, areas which are vegetated, could be maybe cropped lands, not exactly rural, agricultural areas. Vegetation moves, and so the scattering is totally irregular and unpredictable. So things like this tree moving around will give us a complete loss of coherence because there's very little scatter coming back to the sensor. Whereas the actual ground, the crop on the ground, slightly more coherent. So in addition to the point persistent scatterers that we get from buildings, which are these long, tall, dark blue spikes here from the buildings, there is another layer, statistically less sort of strong in their scattering behavior, but they have a certain predictability about them. So we try to understand and retrieve the patterns of scattering behavior, the phase signature of these slightly less strong but still persistent scatterers. We can improve the InSAR results, and we do that by comparing the phase in time and space. So these rather complex and colorful looking things in the bottom are sort of matrices, if you like, comparing observations with each other and with other every conceivable interferogram in the stack to look at the way the phase behaves in time and space. So this is a rather more stable, predictable pattern, whereas on the right we have a slightly more chaotic pattern where there's lots of phase changes, and we can characterize these in time and space to help us understand the scatterers on the ground a lot better. And so the result of that, if we go back to South Wales, here's our PS map with lots of black areas where we have no points. And here is the result when we retrieve the natural scatterers on the ground. So we have far more data. And yes, it's all green, which means it's not moving generally, but there are some blue areas, distinctly blue areas, which are rebounding after all kinds of mine workings have ceased, and groundwater is probably responsible for that. And there are also some red patches, which are quite interesting. I'll show some of those. So here's one, for instance. These are some mine workings and some backfilling of an open cast coal mine from the Industrial Revolution, and the spoil, the material that's been backfilling is settling, and that's the red colours. So this material is compacting over time, and there are some areas of heave as that shifts slightly, or maybe it's wet and it's rebounding a little bit. But this is an area where you would, with PS InSAR, you would get very few retrievals. So we're seeing a very vastly improved retrieval. Here's another example of again backfilling of an old mine, open cast mine, and the materials are subsiding. In fact, two is a quarry and a mine. So excellent retrievals. And here's actually a landslide occurring in a neighbouring valley. Again, it's heavily vegetated, and the council know about these landslides, 2 of them on the side of the hill. The blue colours here are because this is a single observation from, I think it's the ascending arm, and the blue indicates that it's rising or getting closer to the sensor. So these actually are the toe of the landslide heaving slightly, bulging toward the sensor. But they're both active landslides. And you can see the point density is really quite extraordinary. We would not normally expect to get any points here using PS. Switching out to Mexico, I want to show you quickly an example of a similar processing chain called SQUISAR from collaborators in Milan to the problem of looking at a volcano. This is probably the most challenging rural environment. It's a very active volcano. It's raining down ash and tephra quite frequently. There are no point persistent scatterers. It's entirely distributed scatterers from the rocks and the lavas and the pyroclastics. And this is what we get for the exposed edifice of the volcano. This incredible map of the red colors here are recent lava flows in the last 4 or 5 years subsiding, and the rest of the edifice is relatively stable, but you can see these red sort of tongues are lavas. And if we look at the time series, we can see that they're subsiding very nicely. The subsidence is sort of it's fairly steady, sudden initially and then slowing down. We can also forensically analyze some complex patterns in the upper edifice of the volcano, and you see that it's subsiding and then rising and then subsiding again, but generally subsiding overall. And we believe these are things like gradual periodic dome inflation, magma injection and dome inflation. And then on the other side of the dome, we see a really strange pattern with steady subsidence, but with some rising and falling on a very short time scale. Now, this might be passed off as being noise, but actually these are caused by periodic gas buildup and then sudden escape. And if you look at them carefully, they rise gradually and fall suddenly. And we've tracked them and compared them to ground observations, and they're real. They're geological, have geological origin, and they're measurable. They're not noise. So you can really, you can really dig into this data and pull out some really complex geological phenomenon. And if we look at the decomposed vertical and horizontal components, you see that the entire upper edifice is not only subsiding vertically, but it is moving to the west. These red colors here are western movement. And so this raises an issue about stability and potential collapse of the volcano, the upper edifice of the volcano. So there's lots of hazard implications, very important. And we can forensically analyze the patterns of subsidence and patterns of movement. We can also look at how fast they're moving. This is acceleration derived from these scatterer measurements. So we can see that some parts, like the lava flows, that blue area, subsiding but slowing down, whereas the yellow area at the top is fairly steady and then suddenly begins to accelerate in its subsidence. What this means geologically, we don't know. We're working with people in Colima in Mexico to try and understand what these data mean, but they are fascinating nonetheless. And then if you move further north to the city of Guzman, well, they've got terrible troubles because they're sitting right on the edge of the rift, and the city straddles a major geological fault, and they're having all kinds of troubles with subsidence throughout the city. And plenty of work has been done. It's the subject of a large atlas on geohazards in urban areas. And if we forensically analyze this, you can see it's not as vertically moving, but it's also this fault. The hanging wall of the fault is moving to the west, and it's a bit more complex on the other side, not quite so many points. But this is how it relates to the volcano. There's the lava flows in the south, and the city has got huge problems in the north. And if we look here, so this area has really steady subsidence in the city. If we do a cross-section across the city, what you see actually is basically the subsidence caused by two rift faults on either side. One is bigger and moving more rapidly than the other. That's the fault on the east. And if we do another cross-section down through the subsiding area, this blue cross-section here is actually charting the displacement envelope of the large fault. So that's something like 5-6 centimeters over a 3-year period, which is pretty substantial. So those are the examples I have from some of the work we've been doing the last few years. And new developments now. One is an improved atmospheric phase correction. Robert is working on high resolution atmospheric models coming from the Met Office to try and improve the correction of atmospheric effects, the tropospheric effects, water vapor, etc. These are well known for causing errors in InSAR results, and many of the current models have flaws. Mainly they assume that the effect of the atmosphere is spatially correlated, but very changeable in time, and that's not necessarily always the case. And so Robert's using this high resolution multi-level model, which assumes a slightly different effect at different altitudes, and also taking into account the topography using a DEM. And his results indicate a high degree of spatial heterogeneity across any particular SAR scene. This is one burst of Sentinel-1, and you can see a lot of really complex patterns, which we think are to do with clouds, and other weather phenomenon. And the size of the shifts that have been caused by the atmosphere are on the order of a centimeter. So these are pretty significant errors that are embedded in everybody's InSAR data. So this is a tremendous improvement, potential in improving our InSAR results even further. And we're also working on using this distributed scatter, a long time series InSAR, to improve our ability to extract soil moisture information. Soil moisture is usually misinterpreted because vegetation is often on wet ground, and what's actually being picked up is the water in the plants. So what we're really after is the change in the dielectric properties of the soil, as they increase the phase delay, and so that has to be taken account of in order to improve the ground measurement. So in trying to improve our ground measurements, we have a byproduct, which is soil moisture, and that has lots of implications for all sorts of other important fields of endeavour. Another byproduct in trying to improve the ground monitoring capability is that we can extract vegetated biomass. We can classify crop types by characterizing their behavior in different polarizations, but in time and in space. And this has massive implications for the way that land cover mapping is done. So we're quite excited about this work. And here's just sort of a tester. South Wales mapped as never been seen before. This is the product of our SAR phase characterization in space and time. In this wet, it's really wet. I know, this is where I come from. It rains a lot and it's very green. And what you see here is all the different kinds of vegetation. So the upland heath of the Brecon Beacons National Park is in blue up here. And this complex multicolored patch down here is agricultural land, and a variety, and the dark red is forest. So this is an extraordinary map, which is kind of an accidental byproduct of our endeavours to improve ground motion monitoring. So we're quite excited about that. And then one last thing, Anthony's work on developing drone SAR. SAR imaging from drone is not in itself difficult. You know, we're interested because engineering firms are wanting flexible solutions to monitoring moisture in all kinds of settings, infrastructure settings, engineering settings, moving towards almost kind of ground penetrating radar. So Anthony's doing lots of experiments with frequency and antenna design. But as I said, acquiring a SAR image from a drone is not so difficult, but being able to conduct InSAR, that's challenging, because we have to basically make the drone fly on a path, a repeat path, which is as close to the previous path as possible within something like 1 meter. And that's quite hard to do. So anyway, that's an ongoing development. And of course, using drones for InSAR is probably has quite a narrow field of application. It may not have, you know, it may prove not to be terribly successful, but it's something that's worth looking into. So that's all I have to say. And so just to conclude, really, we're really excited about our developments and our achievements in improving retrieval areas. So we've come from monitoring urban areas with point persistent scatterers, and we've developed a way of really effectively extracting more data in rural areas, and also in so doing things like extracting vegetation and soil moisture. We're currently writing the UK guidelines on Earth observation and InSAR in civil infrastructure. It's not finished yet, but it's underway. So it's a pleasure to be working in this team, and it's very exciting. And we can't conduct persistent scatter InSAR on Venus because we won't have enough data. But the improvement of these processing tools is definitely being done, you know, with other applications in mind. And all these things are related. So anyway, thank you for your attention. And if you have any questions, I will endeavour to answer them.
Thank you, Dr. Mason. We really enjoyed your talk. I'm going to check for questions. I asked everyone to type in their questions in the chat. Mohammed Zakzouk is asking, he says, thanks for all the presented cases. I'm asking if there are manuals explain the presented approaches in detail and software recommendation to do similar studies.
Okay. Well, most of what I've shown has been published. So there are papers explaining what we did, exactly what we did. Some of the work, the things, the kind of new developments, that's not yet published, but is coming. I don't think there's anything in there that hasn't been published. Any case studies anyway. Oh, perhaps the Poland has not been published. But there are lots now of cases of the use of InSAR on tailings dams, particularly since the terrible disaster in Brazil. It's very much a hot topic. In terms of software recommendation, well, so there are a number of processing chains on the market. Some are proprietary and top secret, and ours is a bit top secret at the moment because we haven't published it yet. but it's in writing now. There are to have a go at this. You need either SARscape, EnViSARscape, or I think ERDAS-Imagine also processes SAR data. So those are your sort of entry points. And our SAR processing engine has been built on SARscape initially, and then has been modified and customized. So that's how we started. You can use the Snap tools, the ESA released free tools in Snap. They are excellent, actually, but you can't do time series in SAR using those tools. That they'll allow you to produce interferograms. Anything else? In Cyprus, there is a great need. Sorry, I'm now reading the chat. There's a great need to monitor cracks in roadwork. Yeah, I bet. Yes, absolutely. You know, you're relatively semi-arid, aren't you? Certainly the tools, the improved tools in rural areas, should that you can do this without any difficulty. I would think that you're, as an environment, probably similar to Mexico. So that case in Guzman City in Mexico, it's sort of vegetated on the hills, but pretty dry. I would think that you'd have no trouble in monitoring. Perhaps get one of our students to work with. To my knowledge, there are limitations in monitoring flat land movements within SAR.
The audio.
I'm not quite sure I understand the question, Marius. Thanks for your presentation. Ask about what is the recommendation for challenges to monitor the land subsidence in the Nile Delta? Somebody's already probably doing it. I think we should have a go. We started looking at not quite the Nile, but we started looking at the Afar Triangle in Ethiopia. We wanted to resolve the active rifting there, but I would think that there's a lot of vegetation growing along the Nile, so that may be troublesome, but I think it's achievable. Yeah. What is the cost of UAV with InSAR on board? Good question. Well, the drone that we have is a fairly standard DJI Matrice. It cost about €5,000. The kit to build the antenna and the radar instrument, relatively cheap, off-the-shelf products which he bought and is building himself. So pretty low cost. I mean, that's one of the reasons for doing it. Is there a limitation in case the magnitude and the speed of the land displacement phenomena are excessive? Yeah, absolutely. So if you if the magnitude of the motion exceeds half the wavelength, or even a quarter of the wavelength in one go, yes, you'll lose coherence. So InSAR is particularly good and can resolve very large movements, but only if there is a gradual ramp of displacement. So for instance, where there's a big fault, an earthquake on a large fault, in the very narrow area along the fault where the motions are chaotic and very great, then you lose coherence. But where on the kind of the ramp either side of the fault, that's that gentle movement of the ground, the gentle change, that can be resolved even if the size of displacement overall is quite large. Have I tried DS InSAR with waste fields? Yes, it would be possible. Yes, that's something that we are looking at, definitely, and particularly with DS, because if you've got a waste landfill and it's vegetated on the top, you really need to put corner reflectors to help monitor if you're using only point persistent scatterer techniques. But if you use distributed scatterer techniques, and you can potentially monitor without doing that. There are other techniques. Persistent scatterer InSAR is just one of a series of techniques. There is another referred to as short baseline separation, and that is a kind of a spatial averaging. So that can retrieve more points in rural areas, but with less precision. So the distributed scatter approach is a kind of intended as like a compromise. It brings the spatial acuity of point scatterer interferometry and the ability to retrieve over rural areas together into one tool. So it's probably the best thing to do to monitor waste landfills. Did I catch all the questions? Oh, the only one I didn't get was Marius's question. I didn't quite understand the question on monitoring flatland with no, I think it's fine.
Marius has clarified further.
Oh, where?
Yes.
Going back with the second one. Oh, I missed it. Sorry, the limitation of the latitude. Oh, yeah, about that. Okay, fine. Okay, hope I've got that. Good. So, wow. Any more? I think that's it.
Do we have any more questions for Dr. Mason?
What? Oh yeah, I think I answered that one. It's it's a few thousand euros for the entire thing, the UAV and the sensor design. Less than 10,000. How does it compare with Central? Much more expensive. So I mean, that's the advantage of using Earth observation satellites, because the cost is born years ago in the launch, the design, and those data are free. If we then talk about X-band SAR, the commercial satellites owned by a variety of companies, TerraSAR X or Tandem X, and there are others now, then the data, there's a cost associated with the data, hundreds of euros per scene. So that if you want to do operational monitoring in an urban area, you need to really expand. You get more points, greater sensitivity to small scale targets. Have I used Pulsar Pro to estimate? I haven't. No, I haven't. I can say I clearly haven't done that. I don't know anybody, not in my team, that has, I'm afraid. Can't help.
Okay, we don't have any more questions. I would like to thank Dr. Mason and thank everyone for joining us today. Oh, excuse me, we have another question from Professor Hajime, please. Which is the best and more efficient way to teach SAR in students with non-engineering backgrounds, such as archaeologists?
Well, it's difficult. There's quite a lot of maths, but the concept is really simple. The trigonometric concept is really simple. So if they can grasp that, even if they don't really understand the maths, if they can grasp the geometry and the principle of extracting the fraction of phase, which is ground motion, you can teach them with very graphic sort of illustrations. And our students are very numerate, but even sometimes they struggle with can you really do that from 700 kilometers away? So I think the concept is so simple that they'll get it. even if they don't have strong maths background. I've got lots of lovely slides you can have.
Okay, well, thank you. Thank you, Dr. Mason. Thank you, everyone who joined us today. We will be sharing the recorded video with you later on today or tomorrow. And thank you again for joining us. Enjoy the rest of your day.
Thank you very much for the invitation.
Thank you.
Thanks for coming.
Thanks, great.
Bye. See you tomorrow, dear Phantos.